What's going on, Sensation?
Technical difficulties.
Oh, is your camera not working? Uh-oh. Uh-oh.
Oh
Uh-oh.
no, the camera's here. The camera's here.
Oh, no. Oh, were you doing some streaming this weekend while I was out?
I was trying to, but
This is cool. It's kind of like upside down.
Wrong with my machine.
Nice. Oh, I can see it now. Okay, cool. Ooh, looks like you're doing expand and I have to read upside down though. What's up, Ace? What's up, 1K?
That's not fun.
Oh, there we go. Oh, I love all the memes you have on the side. There we go. Now I can see it. Nice. Oh, congrats, dude. You got 200 followers. Good job, dude. That's pretty cool. Nice.
I keep losing.
I know. I mean, I like gain them, lose them. I find if I just like raid other people, usually I get followed by the people in their stream, which is pretty cool. Oh, nice. Okay. Yeah, where was I? I was in the desert this weekend because I had a show I was playing. Let's see if I have any videos from it.
Who the fuck is Yomo?
Yomo? It's a person. I don't know. Yomo? Someone. Let's see. This was it. Yeah, someone took some pictures of me. This is pretty cool.
Why were you back in the desert anyway?
I was playing a show. Oh, this is me. I was playing the cello. I was playing the cello. This is the first time I did like cello and that was pretty fun. Yeah, so I was like DJing and playing the cello at the same time, which was kind of entertaining. It's the first time I've done that actually, and it was very interesting to like there are two brains I have to put on. I have to work because I have to work the decks, which is DJing, and then I also have to play a cello on top, which is it's a different type of music. So I don't know. I think next time I do it, I'll probably pre-plan a little bit more of the DJing so that I can focus more on the improv of the cello, because I was improving the cello and also improving the DJing, so it becomes like a little too much. It's like I was at my brain's capacity. Also, because I've been up the night before until I think 8 a.m. or something. Yeah.
The technical term is counterclock.
Counterclock. Yeah, is that what it is? Counterclock.
No, counterclock.
Yeah. Canter clock? Sorry, what was it called? Also, I apologize.
Oh
my voice is gone.
She sells by the seashore. Can you hear me now?
I can hear you now, dude. Yeah. Counterclocks?
Okay, I said we call it counterclock.
Okay. You gotta spell that for me. Wait. Oh, counterclock?
C-U-N-T.
Yeah.
O'clock.
Oh, cunt o'clock. Okay, gotcha. Right. I okay, this is actually a thing. Well, apparently it's also for drag queens.
Yeah, no, it's really not. Just that's Reddit for you, though.
That's Reddit for you. Well, that makes sense, I guess. I
think the whole world agrees at this point that Reddit is just a cesspool.
Yeah, it's turned into the next what we call it, like kind of like 4chan, right?
And see, 4chan was good. No,
4chan was never good, dude. That's the meme. 4chan was never good.
You can't run around shouting the N-word.
Yeah,
Can.
you can't over there, yeah. My light's like kind of messing up. Anyways, yeah, so I'm back. I apologize, my voice is gonna be kind of gone today, but I will try to help as much as I can. It'll be back to normal tomorrow. I was screaming on a microphone for a lot of the time, and then the dust and everything it's not good for my vocal cords. No. But it's fun. I enjoy it. There's some good people. It was one of my friends through the event, and I ended up helping out a lot of it. It's actually kind of cool. I got to, fix things. A lot of times, like, electronics were breaking, and then no one was really there to, like, fix it. So I just stepped up and just started fixing it, I guess.
Fix it.
Fix it in post. That's always a joke. Anyways, okay, cool. Looks like we have a couple questions to go over. So let's start off the stream and we'll get into it. Okay. 3, 2, 1, and go. All right. Welcome to an office hours. My name is Dr. Gold, Sexual Education. Streaming helps you with math homework, science homework, all sorts of fun stuff. It looks like Sensation's actually doing math right now, isn't he? Yeah. What are you doing? What is this expanding polynomials or factoring?
Factorizing.
Oh, okay. Factoring is very useful, actually. Okay. Oh, this is your...
So this is C1.
C1. Is that... So, yeah, I got you. I could make it... Yeah. So, C1. Is that like A levels, O levels? What is that? Or is this the GCSEs thing? Oh, it says A level. I'm dumb. I'm going to be kind of slow today. I didn't sleep as much as I should have. Algebra and functions. Okay, cool. Nice. Yeah, I have a video on inverse functions I need to put out. I meant to do it before I left for the desert, but I got busy. But yeah, that's good stuff. I have to teach a student later tonight on how to factor functions, but also how to have you done polynomial long division, Sensation?
You'll have to. What exactly is that?
So you can divide numbers, right? If we want to do big numbers, right? I don't know. Let's say we want to do 543, right? Divided by 3.
Okay.
Yeah. Well,
yeah.
Yeah. You can do it also with polynomials. So if you have, for instance, 4x to the 4th plus 3x squared plus 2, and you want to divide it by I don't know, let's just say x plus 1, you can do that as well. It'll get you a result.
Huh.
It's useful. I'll show you why. So, let's say, for instance, I have, x to the 3rd plus 3x squared plus, let's say, x. Actually, let me change some things here. Let's do that. All right, so then let's make that -1. So that's going to be -16 plus 3. What's up, Serena? How's it going? First time chatter. How'd you find us, dude? Welcome, dude. Let me think. 16. I have to come up with one that works, and then this would be plus 12. And then let's say
I've seen that person's name before.
You have? Well, probably
Somewhere.
in your town. Yeah, probably in your town somewhere, dude.
Sarito Hakenji. That's it might be similar to my name, as you probably know. But,
Yeah, there we go. Sarino Hakenji. Is it Japanese? I guess, right? Yeah.
Sarito Hakenji, maybe.
Yeah. So I mean, for one thing, for these, we could ask how to factor this. You know how to factor stuff when it's nice. If it's x squared plus 5x plus 6. This factors out really nicely, right? To x plus 2 times x plus 3.
Yeah.
Yeah. We know the rules, right? I'm looking for what multiplies to 6, adds up to 5, and that's 2 and 3, and that's how this works. Now, where this can get tricky, right, is let's say I have something like this, right, which is already out to the power of x to the 3rd. We don't know any real easy tricks to factor this yet. But what we can do is divide it by what we think one of the factors is, and then make it simpler. Because every time you divide something, right, here with powers by another thing, it's going to drop the power by a factor of 1 at least. Okay.
Mm-hmm.
So, for instance, in order to do this, we want to end up writing this as a bunch of these, hopefully, a bunch of factors. 3 different things with x's in them. Because then there's some numbers in front of them that will eventually get me to this.
Wait, I have seen this before.
Yeah.
It was super advanced stuff.
Yeah, so I'll show you. It's funny. I'm going to teach this again to a student later tonight, so it's actually kind of a good warm-up for me to do this. All you have to do is you have to first guess what one of the roots would be. So roots are always what causes this thing to be equal to 0, is what we say. Because at the end of the day, I want to do something like x minus a root times x minus a root, right? So that whenever I plug in the root for x, this becomes 0.
Mm-hmm.
And then the whole thing becomes 0. So one way to do this is to try to guess what the root would be. And the way you can do this is called the rational root theorem. You take the factors of this thing, we call this like P, and you take the factors of this thing, which we call Q, and then you do P over Q. So the factors of P, which in this case are 2, that's just be equal to plus or minus 1, plus or minus 2. And then the factors of Q are also plus or minus 1 and plus or minus 2. So P over Q ends up being plus or minus 1, plus or minus 2, over plus or minus 1, plus or minus 2. And then you have to do all the combinations of these, okay? So for instance, I could have this 1 and 1. So that's going to be plus or minus 1. I could have a 1 on the top, a 2 on the bottom. That's going to be plus or minus 1/2. And then I could have a 2 on the top and a 1 on the bottom. And that's going to be plus or minus 2, right? Technically, I could have the 2 and the 2, but that's the same thing as this. It's double counting, so we don't need to do both of those. Okay.
Is it a lot of it's a 1 or something?
Yeah, that just has 1, so that's fine. So what I do next is I try to technically I have to check all of these to see if like one of them will work. But I'm gonna be kind of sneaky here, and I'm just gonna say, okay, I'm gonna guess -2. And I'm gonna try plugging it in. So if I plug -2 into here, right, we get 2 times -2 to the third plus 3 times -2 squared plus -2 plus 2. Okay. And if I did this correctly, this might turn out to be something nice. We'll have to see. So this is -16, and then this is plus 12. And then this is going to be, oh, you know what I needed to do? I need to make this a minus x. Let me change this and change this minus x. Yeah, minus x will work well. Okay, so then that's going to be minus -2, so that's going to be plus another 2, and then plus 2. And so what this gives me is 0. Okay? So that tells me that -2 is a root. Okay? Yeah, we can do Cardano or maybe long division. Yeah, so I'll show you how we call it synthetic division is the other name for it, Sereno. But so this tells me that -2 is a root. Okay, so that means I can write this thing as x minus my root, so x minus -2, which would be x plus 2. Am I say? Yeah, I just got back from the desert. My voice is toast. Yeah, I was playing a show out there, and I always end up losing my voice because it's dry, it's dusty, and yeah, I'm usually on the microphone a lot. So I know that this is now x plus 2 times some other stuff. Okay. What I want to do is I want to figure out what this other stuff is, right? Because I
know that. I know that this. Thank you. Ace got baby voice. So at least my raspy voice will now be this baby voice.
Why?
I wonder what it sounds like. It's very terrible. Thank you. I do need to drink some water, actually. Thank you. Yeah. More water. Drink more water. Yeah. Alright, so let's think here for a second, right? Okay. How can I figure out what this is, right?
Thanks, Laz. I appreciate you, dude. Let's think of this as like, let's say this whole thing was like A, right? Was equal to B times C. If I wanted to figure out what C is, right? If I want to figure out what this is, right? There's a way to solve this algebraically, right? I could just divide both sides by B, right?
Yeah.
Because then this would go away, right? And that would just give me A over B is equal to C.
Hang on a minute. B minus C divided by C over you end it with.
Oh, this is time. Sorry. This is B times C.
Right.
B, yeah, my bad. Right, because this is times.
I'm still not used to reading it like that.
Yeah, I know. Well, are you used to reading it like this for this B times C?
Well, no. Look at the book. It's everything's still written with the times symbol.
Are you serious, dude? Oh, that's fucking awful, dude. They should never do that. I don't know why we ever teach kids. I don't know why we ever teach it with the X. It's so bad.
But then, from my perspective, I don't know why you teach it the way you do because I've never seen it that way.
Well, I mean, we shouldn't do with the X because X is a variable, right? That gets used, and then the dot is better.
We write it differently.
Yeah. but it still looks.
At times is flat, and X is always curved.
Oh, interesting. Oh, you always italicize it. Oh, okay.
So you probably can't really see it, but all these X's are
Italicized.
big curves.
I see. Okay.
But the time symbol is like a really thin, flat sort of.
I see.
X.
Yes. So you do like this versus like this, probably. Like these are like two different things. Yeah. We eventually end up using the X anyways when we do what's called the cross product. So whenever we end up using the cross product on vectors, we go back to using the X again. Isn't that Chi? I think it is Sereno. Yeah, is this Chi? I think it's technically Chi. But anyways, so this, we can also just use the parentheses, right? We know things that are attached, they're touching each other with parentheses are multiplying. So these go away. And you're just left with A over B is equal to C. We're going to do the same thing here. So in order to figure out what this is, I'm going to divide both sides by this, okay? So, in little math language stuff, let's see what that does. So we get this, right, is equal to, I don't know, question mark. We'll figure out what it is. And we're going to divide both sides. Dun, 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 dun. Yep. Chi, yeah, Chi. It's a Greek letter. It's also the brand of a very expensive hair straightener. Not that I would really know. Anyways, this goes
remember my Greek.
You remember your Greek what?
I said I can't even remember my Greek. It's just too difficult.
Did you have to learn Greek, like as a language?
Long time ago.
Oh wow.
It's the pronunciations that fuck you over, to be honest.
Oh okay.
Alpha, beta, you can't really get wrong, but then
sure.
It's not gamma, it's gamma.
And then like this is rho, right? Or sorry, not rho is this, but but it looks like a fancy P.
I can read it, I just can't say it.
Yeah. Okay, but then so then this is what I was talking about originally. Sensation is we have what's called like polynomial division. I can now divide a polynomial. Poly means many, nomials term. So I have a bunch of different terms over another polynomial, two different terms. And to do this, there's two ways. So we could do some synthetic division, which is faster, but a little bit less intuitive. Or we can do long division. So it's this. So watch, we have 2x cubed plus 3x squared minus x plus 2. Okay, and then we're going to divide it by x plus 2. Now division here works the same as it does for long division with numbers. You always see like, okay, how many times does this go into this? They call this Ruffini's method. Oh, that's cool. What country are you part of, Sereno? I didn't know it was called Ruffini's method. So this looks kind of weird. Like x plus 2, like how many times does x plus 2 go into 2x cubed, right? It doesn't really make sense, right? You're just like, what?
No.
They don't really go. Well, what you want to do is you want to get it close enough. You want to know what we're doing is we're just trying to match the biggest term here to the biggest term here. So I really want to know how many times does x go into 2x cubed? And that answer ends up being 2x squared, because this times this will get me this, right? So then right, I multiply this back through it. We got to remember how to multiply polynomials, right? I got to remember what 2x squared times x is. That's 2x cubed. And then 2x squared times 2 is going to be 4x squared, okay? And then we do the same thing that we do in long division. I then take this and I subtract this, okay? So this goes down, this is 0. 3x squared minus 4x squared is a negative x squared. Okay. So then you have to ask yourself, okay, and then I think technically we're supposed to pull down the x as well. I say, okay, how many times does x go into negative x squared? That's going to end up being minus x, because negative x times x is negative x squared, which is what I want. And then, okay, so then cool. Then I got to multiply both things. So this becomes minus x squared minus 2x, okay? Again, subtract. So minus x squared minus x squared, that goes to 0. Minus x minus... people always get confused with the double negatives here. This is kind of the thing you got to watch out for. Because minus x minus minus 2x is minus x plus 2x, which is the same thing as just x. And then I'm going to bring the 2 down again. So cool, we got plus 2. We'll bring it way down here, actually. And then I ask, how many times does x plus 2 go into x plus 2? Well, that's easy, right? That's just 1. Cool, so you just put 1. And then you get x plus 2. Subtract them, and you get 0, which is good. That means that there's no remainder. And so now, this is my answer for, like, what times x plus 2 gets me to my original thing. So now this whole thing here is 2x squared minus x plus 1, which is pretty cool. So now I've factored this thing that was x cubed into smaller things. And so now we have this. Now we got this. And now this is a quadratic, right? So this is a lot easier to factor. So you can do this a couple ways, right? We could end up doing the quadratic formula. We could do completing the square, or we can do I think some people call it like the diamonds and like the crosses and the sticks and stuff. I don't know, but it's called something like that. But I hate this method, but I sometimes end up just doing the quadratic formula because I don't like it when there's like not a 1 in front of here. It becomes kind of weird. But anyways, yeah, that's how you can factor things. Sensation if they're if they're bigger than x squared, you have to do polynomial long division to break it down into something that's easier to work with. Yeah, I wonder if they'll teach that in your class. I wonder if you'll get to that.
Oh, I should point out there is no class.
Oh right, this is self-studied, but yeah,
it was impossible to. Well, anyway, I'm going to be sat on my own for a year, so that's going to be fun.
Well, we can always help you. Let's see. We have some other. Let's see. I do have some questions. So 1K has a question here. This is cool. Let's see. 1K, are you here in the chat? You want to go over? Or the Po-Sheng-Lo method? Yeah. Po-Sheng-Lo method. What's
the evil Chinese?
The evil Chinese. What is that? The Po-Sheng-Lo method. What the fuck? Excuse me. Let's see if 1K's around. I think yeah, he's doing something with
中国人 Zhao.
Oh wow, and then Taco Cat's got a good question about, it looks like circuits. So we got a couple things. We got this. This is cool. The stop sign. This has to do with like, I like this this lonely sprite of grass. Like what? What is this? I guess they're talking about like a stop sign, like causing a shadow. Yeah, this is a cool question. And then also, this is from Taco Cat. Let's see. The human body offers a very small amount of resistance. That is very, very, very small.
See, I told him about that, and he was just like, he just stopped trying. So,
what you tried to help him with this question?
Well, I didn't. Basically what I said was, "What's Ohm's law?" And he said, "I don't know."
Oh well, he should know it. I mean, that's his whole question.
Well, apparently he knew it without knowing it. It was very strange.
Well, they just memorize stuff. Are you going? Yes, I am. Dennis, what's up? Did you post a pic? Did you? Yes, Dennis did have a question actually. Here, Dennis, you want to do yours? Let's do yours. It looks like wave functions. This is kind of cool. Yeah, here I'll pull yours up. This is it, right, Dennis? And then let me copy it in. Sorry.
Consider two wave functions. No.
It sounds like quantum mechanics. Consider two waves. Which one do you need help with, Dennis? Dennis found us on TikTok. That's cool. I have had a lot of people actually hitting the TikTok because I posted that video 3 weeks ago. The first one, if possible. Okay, let's do it. Let's try it. Okay. A large rock with a weight W suspended from the lower end of a thin wire that has length L. The density of the rock is rho. The mass on the wire is small enough that the effect on the tension can be ignored. The upper end of the wire is held fixed. When the rock is in the air, the fundamental frequency for transverse standing waves on the wire is F air. when the rock is totally submerged in a liquid, the top of the rock is just below the surface, the fundamental frequency. When the rock is totally submerged in a liquid with the top. Okay, cool. It's F sub. Determine the density of the liquid. Once a fully symbolic equation, write a calculator with these solutions. So we got some weights, we got some lengths, we got rho, we got air, and we got the sub. Okay, cool. All right. I think where this comes down from is that, so whenever you have like a spring system, right? Let's just say for a simple spring here, Dennis. Here, I'll make the spring in like red, right? Let's do this. I did add them. No, they're there. Yeah, checking the office hours. I did them this morning. Or this afternoon. If this has a spring constant K, and then this has a mass M, this thing has like a natural frequency. You're good. That it'll go back and forth, right? You're not a dumbass. It's okay, Aced. We have omega is equal to the square root of K over M. So this tells me what the natural frequency is for something that is oscillating kind of like a spring. Dennis, did you know this? Yeah. And where this actually comes from, the wave equation is what it does. I wonder. So is this going to be a damped oscillator? I feel like this is a damped oscillator is what this is, because, all right, when the thing is just chilling on in the air, right? Okay, cool. Yeah, hit some questions. Let me think. Sorry. So when the thing is in the air, you have gravity still fighting it, though, right? But I guess that gravitational force is taken into account. Let's see. We have W, we have L, we have rho, we have F, and we have that. Okay. So I gotta think, if this thing is submerged, then we have an additional force. We have the buoyancy, right? Yeah, the spring oscillator, simple and physical. Have you had to do damped oscillators? I don't think this is a damped oscillator. I don't think it's damped. I think, you know what it comes down to is, I think there's a different like K effective because this thing is in water. So, if for instance, right, we have let's say the block, right? It's like this. Yeah, we had to do damped. Haven't seen much. Yeah, it does deal with fluids. I agree. Okay, so let's see the two versions. Okay, so I have it when it's in air. Okay, so this is, for instance, this is air, and then we can do it when it's submerged. So then we can say like, this is gonna be submerged. Okay. Yeah, so here's the difference, is that, and then we need to use like some water, I guess, to kind of like show that it's submerged, okay? Yeah. We have to think about what the forces are on our block. So in air, you just have the force of gravity pulling it down, right? And then you're going to have kx kind of keeping it up. When it's submerged, I have the force of gravity, right? I have my kx, but then I also have what's called the buoyancy force, right? I have the buoyant force, which is going to be pulling it up. So F buoyant. And yeah, so there's sorry, yeah, my voice is kind of gone. Yeah, it's okay. I was in the desert this weekend. I was playing a show. So anything that is submerged in a liquid is going to have a force that tries to pull it back up. And this buoyant force is equal to, I think it's rho GV, right? Where this is going to be the density of the fluid This is going to be the volume displaced I hate physics. Wouldn't that imply a solution to Navier-Stokes? I think the Navier-Stokes equation is or is that the Poisson equation that's like really difficult to solve? Yeah, that's Navier-Stokes. That has to do with I want to say turbulence, right, and fluid flow. Yeah, and then this is gravity.
I thought that wasn't solved.
Yeah, it's not solved. I think it's like one of the big like Millennium Prizes or something, right? Yeah. Okay, so let's think here. So gravity's the same in both of these, right? The difference, though, right, is that the submerged one has a buoyant force, which is, I guess, kind of fighting, or it's helping the spring, is what it's doing, right? It's making the spring, but the force is always being applied to the left. Interesting. Oh, which is the same with gravity always being pointing down. It just changes what the it just changes what the equilibrium length is, I guess. So I think it changes what like the effective K is. Because now the spring is probably going to seem like it's not as or it's going to seem tighter. Yeah. Because now whenever this thing moves down, it's wanting to be pushed back up. Yeah. Whereas here, gravity pulling it down makes it seem kind of like looser. Okay. So okay. K is proportional to the force, right? It's kind of what we see here, right? Yeah, force is equal to kx, right? So the forces that are acting on something is proportional to what the spring constant is. So I think for this, all we have to do is figure out what like the new K is. I think so. I can also like, let me see if I can, let me do some little background research to make sure we're going in the right direction. I've never seen this question before. I'm just trying to solve it, but let's see. This is 15. Okay. Dun, 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 dun,
Spring.
dun. Oh, okay. Well, there we go. Oh, and do we know the density of the? We know the density of the rock. Okay. Oh, okay. You know, it's kind of similar. This is kind of cool, actually, how this works.
Chug,
Okay.
Chug.
Did it? Yeah, it is an advanced problem. Okay. So I was kind of along the same way. I was kind of going with this. But then I forgot. Wait. We want to know the transverse standing frequencies for waves on a wire. Okay. There's an equation for that. That isn't this. This is. I was thinking like we had a mass and it was bobbing back and forth. They're talking about waves inside the wire that's being submerged. Okay. So what's going to happen here is this is going to change the tension that's on the wire. Okay. So here, this is a cool little side lesson, but to actually do this question, what we want to know is that the frequency, and this is similar. It's similar. So the frequency, the natural frequency for a wire, for waves on a wire, yes, exactly. Yeah. So it's equal to 1/2L, and it's the square root of T over mu. Yeah. Good. Yeah. F is T's. Yeah. That's the tension. And then this is the density of the wire. Correct. Okay. Now, what we have to consider, right, is how this is going to change. So in air, right, T is just equal to it's just equal to mg, right? T is equal to mg. It's just equal to the weight of the wire. So we can just say, and they said a large rock with weight W is a thin wire that has length L. The mass of the wire is small enough that its effect on the tension can be ignored. Okay, but okay, yeah. So here, yeah, this is cool. There's 2 different cases here. So instead of this, one sec. We're going in the right direction, but okay, but there's not a kx anymore. There's just tension, right? And this is no longer a spring. This is just a straight wire. Okay, so that's that. Let's get rid of this. Yeah. Okay. Yeah, so there's no more kx. Okay, but there is still the buoyant force. Okay, so this is cool. And then, yeah, this is a tension. Okay, so here's what we're going to say. So in the case in air, right, T is equal to mg. In the case when it's submerged, T is equal to, it's going to be mg, right, minus F buoyant. Okay? So the buoyant force, it reduces the tension in the wire because, right, it's like kind of propping the wire up. And then what we have to remember, right, is for the buoyant force, that's this. So that's equal to the density of the fluid times gravity times the volume displaced by the rock. Which in this case, right, the volume displaced by the rock, you have to remember this, right? So density equals mass times volume, right? So the volume displaced is going to equal the mass divided by the density. Which, so that's going to be, they're giving us W, right? So that's the weight. So we have to say that's W divided by G over the density of the rock, which is this kilograms per meters cubed. Okay, so that's WG over rho. Okay, cool. So I can say, yeah, for air it's this, submerged is mg minus F buoyant, which is going to be equal to, so mg is the same thing as W. They give you the weight of the rock in newtons. So that's mg is what that is. So here it's equal to W, and then this is going to be minus rho of the fluid. That's what we're trying to figure out. And then we have G, and then it's yeah, times the volume. And then the volume is W over G, and that's the density of the fluid. Sorry, that's the density of the rock. So that's going to be, so here let's call this thing X because we're going to solve for it. That's the density of the fluid. And then this is rho. Oh, this is cool. G's cancel out. Goodbye. Okay. So it's just equal to W minus X over P. Okay. So now we got to compare the two, right? So F air over F submerged, right, is going to be this for the two different cases. And then what we know, right, is that the length of the wire is the same in air and submerged, so that goes away. And the 1/2 is going to go away, right? So this cancels, and then we assume that the density of the wire is the same, right? So that cancels as well. And so we just get that it's equal to the square root of T air over T sub. Okay? And then now we have the tensions, right? So the tension in the air, right? That's just equal to W. And then the tension when it's submerged is equal to W minus X over rho, or P. So, and I think we have everything, right? And I guess we don't need L. Yeah, I don't think we need the length of the rock. Yeah. I don't think we need the length of the rock. Yeah, no, we're good. Okay, cool. Does it make sense so far, Dennis? How we're doing this? And so let's see. F air over F sub. So that's 42 over 28. Yep. Okay, good. Awesome. Just making sure you're with us. Yeah. Because sometimes I end up skipping steps and things don't make sense. And then W is equal to 164. So this is square root of 164 over 164 minus X over, and then density rho is 3200. Okay. Okay, and at this point it's just kind of like calculator stuff, right? I gotta square this to get rid of this, and then I'm gonna do a bunch of stuff in the calculator. I assume you know how to do algebra. Let me pull up my calculator. I'm curious if you have the solutions for this, or we'll see if we get the same solution. Okay. All right, where's the calculator? Okay. So I'm going to do this 42 divided by 28. I'm going to square it. Cool. So that's 2.25, and then I'm going to flip. I'm going to flip it. So I'm going to have 1 over 2.25 is equal to 164 minus X over 3200 over 164. It's just a easier algebra trick. And then we times 164. And then I'm going to subtract 164. That's, that's this multiplying and then this subtracting. Cool. And then I'm going to multiply it by negative 3200. That's a very, very big number. Let's see. I don't think that's right. What do we do wrong here? Frequency of the air.
Well, I don't know.
Oh, 3.2 kilograms per cubic meter. Oh, I said 3,200. Wait. No, that's 3,200 kilograms per meter cubed. Wait, did I use the wrong number? No, 3,200, right? Yeah, I think I used the right number. I did. What'd I do wrong?
Like I said, I don't know.
I don't know. Yeah.
It's not even tax for the kids.
Did I have the right thing here? Sorry, rho GV, right? Density of the fluid, gravity, volume displaced by the rock. Volume displaced by the rock is the mass, right? Which is W over G divided by the density. So it's W over rho G. G's cancel. And that's X. So it's W minus. Oh, I messed up. I needed another W here. Sorry. That's where I messed up. Yeah. What's up, Echo? Yeah, okay. That's where I messed up. There's going to be another 164 here. Oh, wait. All the 164s just go away. So I can just divide both sides by 164. Yeah, hell yeah. Let's just do that. So that's 1 over 1 minus X over 3,200. So what? That's yeah. Okay. Okay. Now I think we're gonna get the right answer. So I had my this right. Cool. And then I'm just gonna subtract 1, and then I'm gonna multiply by 3200. And it's just negative. Okay, cool. So good, yeah. And that gets me a better answer. Okay. So that gets me x is equal to 1778, I guess, kilograms per meter cubed. Okay, cool. That's actually, I wasn't able to start. Okay, all good, all good. Yeah. So yeah, that's the final answer. I got this. So I think that's right. Which is, I think, like twice as heavy as water. Yeah, exactly, right. Exactly, about 1.778 times as dense as water, right? Because, yeah, water has a density of basically, yeah, it's 1,000 kilograms per cubic meter. Anyways, that's a good question, Dennis. Good job. Hope that helped you out. Yeah, you're welcome, dude.
Well done.
Good luck on your test tomorrow. Yeah, good luck on your test. Hope you do well. And always feel free to, yeah, you can come by, ask questions. We help you out. Okay, nice. All right. Let's see. What's up, Equity? And Taco Cat's here too. Or is he in the chat yet? I don't see him yet. He has like, I think he has volleyball practice or something. So let me see. And Taco Cat's not here. Okay. What's up, Equity? Here, do you want to... We can help out with one of your questions, Equity. I think Equity was learning about logarithms, right? Yeah, you're learning about logarithms. Yeah, here. Let's do some fun logarithm questions for you. Let's say logarithm. I have a general question for you. Did you enjoy your undergrad in physics? I'm currently a sophomore pursuing my astrophysics degree right now. I plan on going into higher education. I did. Yeah, I did my undergraduate in at University of Texas, and I ended up doing my PhD at UCLA in plasma physics. And so I enjoyed the research aspect of my undergrad in physics. Some of the classes I really didn't like, astrophysics, for instance. I had to take an astronomy class, and I had like the worst astronomy teacher, and so I got really turned off to astrophysics pretty quick. And also I for me, like, quantum mechanics always gave me a lot of problems. And I think that's just because I didn't have a very solid understanding of the math needed for quantum mechanics. I do now. Like, so now I think if I were to take quantum mechanics now, I'd probably enjoy it more, because I understand it's a lot of linear algebra. It's a lot of matrices and eigenfunctions and eigenvectors. What math is you? Yeah, waves are too. There's a lot of wave functions in quantum mechanics. So it's a lot of waves, so a lot of sine, cosine stuff, and then a lot of linear algebra. So yeah, I didn't enjoy all the classes, but I really enjoyed the research, Dennis. And so that's what got me into doing my PhDs. The research was really fun, and so the classes are kind of like a means to an end. Like, you have to take the classes, you have to pass the classes, and when you get into grad school, you then end up taking physics classes that you want to take. So, for instance, I wanted to do plasma research, so I got to take plasma physics courses once I got to grad school. It's been a blast so far. My astrophysics course right now, we're learning about interaction, matter, and radiation, and so far I have no clue. I have quantum mechanics in my senior year, and I'm pairing it up with a linear algebra course. That's smart. Yeah, good. Yeah, linear algebra and quantum mechanics go very well together, and that'll definitely help you out. I'm sorry, are you in high school, or are you a sophomore in college? Sorry, that makes sense. Actually, sorry, yeah. You're applying to a master's in math. Nice. Yeah. If you want to know, so here, if you're thinking also like more in the math path, wait, not math streamers. Was it streamers? What is the command? Damn it, what is it? I
Ads?
thought it was math.
No.
No, I thought it was math streamers. Oh, there it is. Okay, I just spelled math wrong. Or my keyboard does this thing where it double types. I'm currently conducting research of black holes. Oh, wow. Cool. Varying parameters about it to start orbital mechanics for exoplanets seems scary. Sophomore in college. I'm attending ERAU. Okay, cool. It's nice to see that you all suggest channels. I already followed all of them. Yeah, awesome. Yeah, no. They're our friends. Yeah. We love this whole, there's a big community of other streamers in education on Twitch, and these people are our friends. If you want it, like, so either 2i Pi is currently in a math PhD program, and he's writing his dissertation right now. And so if you have any questions about like upper division math and stuff, he's a great guy to talk to. And then also Penn Center, Brian. Yeah, Penn Center is I think he's the dean, or like he's like the chair of the math department at like a community college. So he also did a lot of like math degree stuff, and he could help you out with that.
I, on the other hand, just tolerate them.
Yes, sensations are lifelong learner too, which is fun. Yeah, I always say like learning has no limits. You know, love Penn Center's yeah. You know, Penn Center is funny. He's trying to learn physics actually. As a little fun little side tangent, during his streams he's now trying to learn physics, and he's a math guy, so some of the stuff is kind of giving him some trouble. Also, the textbook he's using is ridiculously difficult.
Wait, what notifications?
I think he's talking about his Twitch notifications, Penn Center's.
Suicide.
Suicide.
Well, what does it say? I don't understand.
I don't know.
I can't read what that says.
We can look at it at some point, but yeah. So yeah, how do I go? I think I just typed in Penn Center, right? He's also studying abstract algebra from Galleon. Is that a hard textbook? Is he doing it right now? Sorry, is Penn Center streaming? Oh, he's starting his stream in 55 seconds. Okay, awesome. Yeah. Oh, he got 700 followers. Nice.
Penn Center's good. I like Penn Center.
We like Penn Center. Yeah, Brian's a great guy. So, yeah, if you want to ask more higher level math questions and stuff with him, he's an awesome dude. Got a bail. It's okay, Jeff. Yeah. He's way more fun to annoy. Yeah, he's funny. Yeah, we love Brian. Brian's great. So, yeah, we'll shout out to. Can I do that? Can I do that? One sec. Put the T. Yeah, shout out to Penn Center. Yeah, so he's streaming right now. If you want to go check him out, I think it looks like he's doing. This is abstract algebra. So it's like very. This is very high level math that like I don't even touch. But yeah. Yeah, what's up, Equity? Equity, you want to do your question? Here, Equity. Yeah. Oh, nice. I'm leaving. Okay. Abstract algebra is like set theory. Yeah? See, yeah. I want to learn this stuff. It is pretty cool. What's up, Equity? All right, cool, man. Yeah, I think we were learning about logarithms for you. Yeah, you talking about logarithms. We had like some log rules. Where were they? Okay, BAP. But where did I write the rules? I feel like I wrote the rules somewhere. No, not here. Here we go. Yeah, good. These are the logarithm rules. Yeah. Okay. If you don't mind, I recommend Basic Abstract Algebra by Robert Ashe. Okay. Let me pull that textbook up. Actually, I'm actually curious about that. Basic Abstract Algebra. Robert Ashe. Oh, someone has a PDF for it, I guess. Okay, cool. So this textbook.
I also have a recommended book for
Wait,
the person that just recommended you the book. That one.
English. Sensation's so snarky sometimes. He's like, go learn English. So there you go. Yeah.
If I can manage to learn English, you've got no fucking excuse.
I know. Yeah. Equity says, what does BAP stand for again? Yeah, BAP to me, like, I don't know. It sounds like one of those Gen Z things, like WAP or something. You know, BAP. But it stands for base answer power, I think is what it does. You know where I actually got this from? I got this from my friend on Lock. He's pretty cool. He's on TikTok as well. Where is he? Where's my friend? It is on Lock Learning. Yeah, this guy. His stuff does not have zero views. Yeah, there you go. 2.1 million. That's better. Yeah, he does very well on TikTok. Good for him. Where did he do? Was this it? No. This is it. BAP. Yeah.
All right, let's do it. I've always used BAP to remember how it works.
Mention what it stands for, Shawty.
It stands for
base, answer,
and then
power. And I've seen this used a couple times actually. It's I just learned it. I've always just done it like around, but yeah, it stands for base, answer, power. And so, for instance, if you have the log base 4 of 64, or actually let's do something a little bit easier. Let's say I'm doing log base 2 of 8. This would be equal to 3. I Spy's teaching math is some crazy work. Yeah, they call it like brain nourishment, right? It's not brain rot. I don't know. But right. So this is the base. This is the answer. And then this is called like the power. Okay. Because another way to write this is to write this as 2 to the 3 is equal to 8. So this is what's called like, I think the exponential form for like logarithms. Yeah. Why logarithms are cool is they let us look at things where if the scale would be end up being like kind of crazy. So it's called like a logarithmic scale. So I'll show you. A couple things in life are logarithmic, such as here we go. Decibels is a good one. So like how loud things are. Here we go. So maybe you guys haven't seen before what a logarithmic scale looks like. So usually when you're graphing things, right, on a number line, right, it's just like 10, 20, 30, 40, right? Do you see how the distance between everything is the same, right? Logarithmic scales do this weird thing where like it's like big, it's smaller, it's smaller, it's smaller, it's smaller, it's smaller, it's smaller. And then it goes again. Yeah. So it with a linear scale, we go from 0.1 to 100 and it's all separated by like 10, 10, 10, 10, 10. In a logarithmic scale, it goes 0.1, 10, sorry, 0.1, 1, put that back. Go back. 0.1, 1, 10, 100. Okay. So there's more emphasis on it's the power that you're going at. And so logarithmic scales are cool to see the changes in things if like the amplitude is like really big. But yeah, because they work on powers is what we say. So for instance, right, the log base 10 of 10 is equal to 1, right? So I say this is the same thing as saying like 10 to the what is equal to 10. Well, that's just going to be 1. So the answer is 1. Yeah. So log base 10 of 10 is 1, right? Log base 10 of 100 would be equal to 2. And log base 10 of 1,000 would be equal to 3. So when you graph things on a log scale, right, something going up by like a factor of 10 looks like it's going only up by a unit of 1, like on the graph. So that's kind of what you see here, right? This would be like 1 unit, 1 unit, 1 unit, but then the distance between the unit is being multiplied by 10. Yeah. It's cool. So what it does is it allows for if you have data that has like huge values and then it has like small values, this allows you to see the changes at small values as well as see the like what the maximum is. If you view things on a linear scale, this ends up dominating, and you don't get to see like what any of the small stuff is, all the small changes. The cool example for this is here. I can do this on my YouTube actually. If you guys want to see how, like, you know, if we go to YouTube, let's go to my studio. Where's my studio here? I'll show you guys some of my analytics. So yeah, if we look at this, let's look at like all-time views or stuff. Right, and then let's do it in let's do the lifetime. This is cool. So if we look at, for instance, these are all my watch, the amount of people that have watched our channel, like, over the lifetime of this channel. You can see that there are these spikes that happen at certain times. Like here, I don't know, graphing sinusoidals somehow got like 10,000 views in like one day. And so that spike makes it very hard to see any of the smaller things that are happening, the smaller changes. And this is because this is a linear scale. If I made this a logarithmic scale, which I don't know if I can change that here. Effectively, what it would do is it would allow us to see that, okay, cool, there's a big spike here, but I would also get to see what the changes are here. So if I can do this, there you go. So if I focus only on the blue thing, for instance, so only on this blue curve, and I ignore everything else, now I can see how this video has done, you know, better and better during different periods of time. Yeah. But yeah, certain stuff, right? The spike, it causes the graph to be hard to read. So, anyways, yeah, that's why logarithmic scales are cool. But okay, so Equity, for your question, let's have some fun reducing of stuff. Let's say, for instance, I have the log. Well, I want to do like a fun one. Yeah. Let's say we have the log of a squared b cubed over 4c. And I wanted to write that out into a series of other logs. Do you know how you do this? And then here we'll use let's make sure we have all the rules so you can see them. Where are all the rules? Yeah, they're down here. Other key thing is that ln is basically the same thing as log. It's just it's called log base e is what it is. Yeah. So let's see, Equity. How would I do this one? How would I do the log of a squared b to the third over 4c? Let's see where he is. Keanu's gonna be waiting, eating his dinner.
My God, that steak, it's so overcooked.
That's why he's crying, dude. He's crying because yeah. He says, I can't see the question. Okay, cool. All right, can you see it now?
That's not well done. It's congratulations.
Congratulations. You messed up. You messed up your steak, dude. Yeah, Keanu's in the way. Yeah, he's okay. He was waiting for you.
Keanu is never in the way. Keanu is the way.
Keanu is the way. I think they're making a new John Wick. You can write out, there's probably a series of steps for this to work too. Like just doing it all at once would be kind of difficult, honestly. I'm lost. It's okay. Okay. Let's become unlost. Okay. Why are there so many variables? I don't know. Just because there are sometimes. Yeah. So let's remember this, right? If I have the log of something divided by something, that's the log of each thing subtracted from each other. Okay. So what I like to sometimes do is kind of create like boxes. I'd be like, cool, this is gonna be something. And then here, we'll make this a green box, right? Over something, right? So we know if I have log of oh, man, I got rid of my thing. There we go. Okay, if I have the log of something divided by another thing, that's the same thing as the log of the first thing minus the log of the green thing. Okay. So, what we can then do is be like, okay, cool. Wait, but what was the red box, right? So, if we just get rid of it, right? Let's get rid of it for now. I can see that, okay, cool. That was a squared b to the third. And then the green box, oh, well, that was 4 times c. Does that kind of make sense? Yeah. We're not done yet. But yeah, that's like the first step, right? I'm gonna like have these around so I can just like use them later. Okay, yeah. So right, log of something divided by something is the log of that thing minus that thing. So that's one way to do it. All right, so let's put these bricks up. Okay. So now, right, let's start analyzing stuff. Let's start looking at this one, right? How would I break this one up? Because now this is the log of something times the other thing, which we should remember. Log of something times something is equal to the log of the first thing plus the log of the next thing. Okay? So, I can now get rid of what these are, right? So, this was a squared b cubed. This becomes log of a squared plus log of b cubed. Okay? So, that's going to turn this part into the log of a squared plus the log of b cubed. And then we still have minus log of 4c. Okay, what's the next step? How can I simplify this even more? There's another rule that we can use. I see it actually right. It's right up here, right? How could I use that to start reducing some stuff down? And actually, before we do that, let's do this one. How can I reduce the log of 4 times c? Good, yeah. So we got this one, right? Yeah, so let's do this one, yeah. So because, right, of the exponent rule, I know the log of something to a power is the same as the power coming out to the front and then multiplying it. So this is going to be 2 log a plus 3 log b. Good. And then this whole thing becomes, right, log of 4 plus the log of c. And then you gotta be careful here. This is the careful part. This minus needs to distribute onto both things. So this is 2 log a plus 3 log b, and then it's going to be minus log 4 minus log c. So these are all together. Okay, the minus has to hit this one, and it has to hit this, because it was minus this whole thing. Right. So yeah, there you go. Cool. Yeah, so that's how your teacher will ask you this. They'll give you like some log thing with a bunch of like messy, variables and exponents and stuff, and then they'll ask you to expand it out. Next time, it's a good question, equity. We can do it where you have to take this, like you have to take something that's big, and then condense it. That's called condensing a log. And the reason we learn these rules is it makes manipulating variables like easier. Is what it is. Yeah. Okay, cool. Good job, equity.
Well done.
Yeah, you're welcome, dude. Yeah, I know. Yeah, you don't. Yeah, I know the next couple weeks are gonna suck, right? Because you don't have any math classes. You don't have any science classes. Like what? Canada. Tisk, tisk, tisk. Anyways, okay, cool. Let's see. Is 1K still here? 1K, did you want to do your question? So this was 1K's question. And then, I assume they're trying. Yeah. Okay. Cool. All right. Nice. Yeah. Someone said I hoped it was 53 degrees. Yeah. I think they said 53 degrees because that's like the 345 or something is what it is. I think it was 53 degrees. Okay. What would I label the sides? That's a good question. Okay. So they're basically asking for like, what's this side? So we could say like, what is AC? And then what is BC, right? Because you know that AB is equal to 8, right? AB equals 8. We know that. Okay, cool. Yeah. So this is a good question. I mean, so we could have this, for instance, you could, yeah. So the other way, yeah, equity's right. The other way is you can label the side as opposite of the angle. So for instance, this would end up being like side lowercase a. This would end up being side lowercase b, and this would end up being side lowercase c, because it's the side opposite angle, big C. Yeah. So that's another way to write it. So yeah, we could call this like C, A, and then B. If you want to do that, that's fine. We can do that too. Cab. Whenever you have this, so we have a side, we have an angle, but we're missing like another side. We actually know all the angles, don't we? Because we know if this is 90 degrees, right? What does that tell me that this angle is here, for instance? What would angle B be? I know this is 90. So what would
4,090,000,090.
4,090,000,000. A little bit off. It's okay. Close. 180 minus 90 minus 151. Yeah, minus 51. Yeah, that's the proper one. Yeah, because 51 plus B plus 90 has to equal to 180. So the sum of all the angles inside a triangle has to add up to 180. Yeah, good. So good. Yeah. Isn't equal to C. It's technically equal to B is what I would say. So that's the angle here. So angle B would end up being, was it 39 degrees? Yeah.
And the maximum score on a dartboard is also 180.
Oh, that's cool. Like in darts?
Triple 20 3 times.
Triple 20 3 times. Nice. What's that walking stick? Yeah. Okay, good.
And they go mad whenever someone gets the maximum score. I mean, they go mad. You can see it sometime. It's bonkers.
It's like a massive celebration.
So, 180! And then everyone gets them on their feet.
Is that like the goal?
Yeah, pretty much.
That's impressive, dude. Wow. Okay, so we know this is 39 degrees. So to find the sides, we can actually use some cool stuff here. So because this is a right triangle, so right triangle means that there is a 90-degree angle here. Because that is true, we can use trig functions to solve for the different sides. So what you end up learning is what's called like SOHCAHTOA, right? And this is saying that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And that tangent is opposite over adjacent. Okay? So sine of an angle is equal to the opposite over the hypotenuse. And then cosine of an angle is equal to the adjacent over the hypotenuse. And then tangent of an angle is equal to the opposite divided by the adjacent. Do you know these so far, 1K? Do you know what opposite, hypotenuse, and adjacent are for a triangle?
If he doesn't, I'll beat him.
If he doesn't, I'll beat him.
No.
No beatings.
No beatings. Not until morale improves, at least.
Kind of.
kind.
Okay, that's cool.
Oh, he kind of knows. So he doesn't get a super beating. Okay, yeah, cool. Yeah, it depends on the angle. So if this is the angle here, let's say this angle is theta, okay? Then the side directly opposite, that's called the opposite. And then the side that's not opposite, and that's also not the diagonal, that's called adjacent. Yeah. You can think about it like the adjacent is the side that connects to the angle, but it's not the hypotenuse. This is the hypotenuse, okay? Now this would change based on what angle you're looking at, right? If I'm looking at this angle, let's say this is like equal to like, I don't know, like theta 2. Now this side becomes the opposite. This side becomes the adjacent. And this side becomes the hypotenuse. Okay? So it depends like what angle you're looking at. Yeah.
Hypotenuse is always the hypotenuse.
Hypotenuse is always the hypotenuse. Yeah, equity's right. Yeah. Sorry, sensation's right. The hypotenuse is always the hypotenuse. So looking here, if we want to find A, okay, we can look at this angle, right? And see that A is going to be the opposite side, right? And that C here, the hypotenuse, is 8, okay? We know that. So here, if I wrote out the sine of 51 degrees, that would be equal to the opposite of that 51 degrees. So that's equal to A over the hypotenuse, which is C, which we know is just equal to 8, okay? So that's how we could use the 51 degrees to find this side A. We could also use angle B here and use cosine instead. So cosine, remember, is the adjacent over the hypotenuse. So for the 39 degree angle here, right, the adjacent is now this. That's equal to A. And the hypotenuse is still 8. So if I wanted to solve for A, right, I can just multiply both sides by 8, right? Multiply by 8. And so that would get me, that goes away. And here, we can just multiply the 8 over here as well. Well, whatever. Let me move it. Let me move it all over. Right? This would get me that A is equal to 8 cosine of 39. So there's actually 2 ways to do this. If you want to check, they're actually the same. So I pull up my calculator. So let's try doing 8 sine of 51. That's going to give me 6.217 versus 8 cosine of 39. Also gets me 6.217. So you get the same answer using different angles as long as you're using the correct trig function for each. Cool. Right, so that tells me that side A is equal to 6.217. How could I find side B using trig functions? Like how would I do that? 1K. Good. Pythagorean theorem, he's right. So since now you have 2 sides and you know it's a right triangle, you could use the Pythagorean theorem, right? You could say, okay, cool. B squared plus 6.217 squared has to be equal to 8 squared, right? This is the 64. That's true. That's one way to do it. But yes, equity's right. You could use cosine. It is depending like which angle you want to use, right? So here, if we were to use the Pythagorean theorem, right, I have to do this minus this. So I would say, okay, so B is equal to 64 cosine of 51, good, and sine of 39, yeah. And then remember, you have to multiply by the 8 on the front, yeah. So this is minus 6.217 squared, square root. So well, let's just see if we get the same answer, right? So if I do 64 minus this squared, and then I take the square root, that gets me 5.03 for this side. I'm gonna say this is like 5.03. And if we were to do this method, so this would be 8 cosine of 51 degrees is equal to B, or 8 cosine of 8 sine of 39 degrees. Those should both get us what we want, right? So if I do 8 cosine of 51, look at that. I get the same 5.03, right? So same answer. Just two different ways to do it. Yeah, Pythagorean theorem, or you can use sine and cosine if it's a right angle. If it's not a right angle, there's what's called the law of sines and law of cosines. I can teach you that next time if you want. I think that'd be probably a pretty cool thing. So that's a way to figure out sides and angles if you don't have a right triangle. If you have a right triangle, life's usually pretty easy because you can just use the Pythagorean theorem, or you can just use straight sine and cosine. Yeah. Nice. Good question there. Okay, I like that. Okay. Yeah, you're welcome, dude. Nice. Good. Yeah. So, yep. Nice. Okay, cool. Let's see. I think we got. Yep. That's a throwback, dude. I don't think the kids know about that one. Yep.
They don't know about the Sesame Street aliens. Oh no, we're gonna tell them.
We gotta show them. We gotta show them. Show them. Yeah.
This is a fizzy tablet and some water.
Yay! Fun math, science lanes. Oh my god. Okay, whatever. Oh my god, dude, this is too funny.
At 16, we used to get really stoned and watch this.
Not Mars. Nope. Earth. Yep.
Dude, this was a kid. This is a kid's show. This is Sesame Street.
Hello.
Greetings.
Hello. Hi there.
Nope.
Earth. Okay. This is too much. This is too funny. Let's see. Wait. Walking Six says, with a right triangle, don't you drop? With a non-right triangle, don't you drop an altitude? You can if you want to split it. Yeah, into right triangles. Yeah, he's talking about like, so, if for instance you had a thing that was not a right triangle, let's say it was something like this. Yeah, you could. Yeah, he's saying drop an altitude. So I guess would that be this? I think you have to drop two altitudes, right? Because that would make that a right angle. Yeah, there is another formula. Yeah, so if you have something that's not a right triangle, and let's say this is like A, B, C, then this is side A, this is side C, this is side B. You can use what's called like the law of sines. So you can say like the sine of angle B over side B is equal to the sine of angle A over side A is equal to the sine of angle C over side C. Yeah, that's the law of sines. And then there's the law of cosines, which is... So one of them you use for like when you have sides, if it's like two sides and two angles. The other one is like three sides and one angle. But yeah. And I think this comes from what Walking Stick's talking about. I think it is dropping in altitude is what it is. Equities as have I seen Oppenheimer? I did see Oppenheimer. I really liked Oppenheimer. It was kind of like the rock star physics. There were so many rock stars in that film. Like people who did a lot for physics were in that time period of like the Manhattan Project and stuff. There's Fermi. There's Oppenheimer, of course. You had Feynman as well. He was like only like a very young Feynman. Yeah. Why was he getting interrogated? Yeah. So I didn't like that they had that. It felt kind of weird. I felt like they should have just focused on Oppenheimer, like making the bomb and like cool. But then they had this whole backstory of him like getting interrogated. So I think it was the 50s and 60s, there was what was called the Red Scare. So
McCarthyism.
McCarthyism, yeah. So after World War II, the two major superpowers were Russia, right? Or at that time it was called the USSR, and the United States. And the United States believes in capitalism and, democracy, apparently. And the USSR believed more in communism. And they're two completely different ideologies for like how a society should function. And so people in America were scared that other countries were going to start switching over to communism, and they started demonizing communism as like this terrible thing, which sometimes it is. I mean, like anything,
Actually, it was slightly more than that.
Oh, it was more than that. What was it more?
Basically, the rise of Nazism was as a result of communism itself, and so they were concerned that America would become a fascist nation to go against communism. So the best way is to just stomp them all out.
Oh, interesting. Okay, I see. Yes. Okay, so
if it
that's
wasn't for the
fascism.
communists, World War II would not have happened.
Interesting. Oh, I didn't know about that. Okay. So
because the communists were really, really screwing up Germany after the First World War.
Okay.
They were doing it for quite a long time. Basically, the National Socialists all got together and went, no.
Okay. So we were
the wrong people took it.
So we were more afraid of like creating the Nazis again, and so we saw that communism was a driving force in Nazism, I guess, like becoming a thing. So we're
I should also point out quite a lot of Nazis in the US at that time.
Interesting. Okay.
They were all grabbed from Germany during the Second World War.
We did on the Manhattan. Yeah, exactly. We grabbed a lot of the Jewish scientists and whatever Nazi scientists and stuff, and there really was communist infiltration. Russia also had the bomb due to 2 spies. Yes, and they got executed. Actually, I think it was a man and a woman. It was a couple, right? Wasn't it? What was it? Is that how it worked?
I vaguely know that story. Yeah, I think it's right.
Was it a couple? So Russian spies couple nuclear bomb. Yeah. Oh, and they're in the Oppenheimer film, I think, right? Rosenberg?
Jesus Christ, that's got to be a joke in and of itself.
Oh my God, yeah, Rosenberg. That's too funny. Yeah. So yeah,
the Russians have always hated the Jews.
Yeah, Russians hated the Jews, but they were definitely Jewish. Yeah, they were executed by an electric chair, dude. Like Jesus Christ. But yeah, espionage. Yeah, so. Yeah, so right after World War II, there was this race, this arms race, and Russia wanted to get the technology as well. So, yeah, communism, evil, bad, and I forget what was. Yeah, Julius and Ethel Rosenberg. Yeah, we pulled it up. Why? Oh, why was he being interrogated? Okay, yeah. So Oppenheimer was being interrogated because his wife, I think, used to be a communist, and they were worried that he was also a communist and like might be a spy and might be like working for the Russians or something. So that's why he's being interrogated. And it's I think the movie kind of gets at this terrible thing of that, like, he did so much for the US to develop the bomb and like whatnot, and then his reputation got kind of tarnished because afterwards they started attacking him thinking he was a communist. So I don't know. It dives into like this, the country that should be thanking him for like all his work is now like going against him. Yeah, at Sing Sing in Austin. Oh, that's the prison. Yeah, I see it. Sing Sing Correctional Facility. Yeah. Anyways, yeah, there's a lot of cool stuff. Yeah, I wasn't. Yeah, the Robert Downey Jr. part of that film is kind of like boring, but yeah, it's that he's being interrogated because they think he's a communist. I'm pretty sure. Let's see. Let's do Taco Cat's question, then I'll probably end the stream off. Let's see what we got. Human body offers a very low, small amount of resistance, let's say 1 milliohm. Okay, so anytime I start seeing these, like milli, whatever, we should put these in what's called scientific notation. So I can say that 1 milliohm is the same thing as 1 times 10 to the minus 3 ohms. And that's equal to, we're going to say R, which is resistance. And then gigavolt, so giga is 10 to the 6. So I'm going to say 1.21 gigavolts. That's equal to 1.21 times 10 to the... No, so giga's times 10 to the 9, sorry. Mega is times 10 to the 6. This is 10 to the minus 9, 10 to the 9 volts. Okay. And that's going to be a voltage. The resistance. Okay. So it says, lightning bolt has this much voltage. This is your resistance, and they want to know if how much current is going through your body if you get struck by lightning. So yes, this is what Sensation was talking about, Ohm's law. So Ohm's law says that voltage is equal to current times resistance. Resistance is futile. Right? Yeah, good. So if I want to solve this, right, I just say, okay, 1.21 times 10 to the 9th is equal to I, this is what current is, times the resistance. Yeah, this is also written as V is equal to IR. Veer. And the resistance, we know what that is, right? That's the 1 times 10 to the minus 3. Okay. So here we can get rid of this. We don't need this anymore. So now you just move this over to the other side, right? And I get that current is equal to 1.21 times 10 to the 9th divided by 1 times 10 to the minus 3, which is going to end up equaling what is that going to be? That's going to be 1.21 times 10 to the 12th amps. So that's a lot. Yeah, wow.
Who asked this
Yeah.
again?
Pardon?
Who asked this question?
Taco Cat.
Taco.
So yeah,
I don't think
it's okay. Yeah, I think he's at volleyball practice. So anyways, yeah, that's a lot. So that's like death. Uh-oh. Death.
Death comes for you.
Yeah, so yeah, because only 50 milliamps will stop a heart. Yeah, it's very small. Okay. Nice. Okay, that's cool. All right. Without any questions, I can end the stream off. Also, I want to get some rest before my next student I got to teach. Okay, cool. Okay, awesome. All right, let's end the stream off. All right, thank you everyone for coming to office hours today. Appreciated all your questions. Big thanks again to our server boosters. Thank you, Laz, Noise, Equity, Ash, Alprince, Hypatia, 1K. I think I have to give out another Discord Nitro next or tomorrow because I think we're running out of our tiers again. But anyways, okay. Our next stream is gonna be tomorrow. My voice will be back, and I will be in much more alive spirits. So I literally got back today from this concert that I was playing. So I still need to rest, and my vocal cords need a break. So yeah, our next stream will be tomorrow. That's gonna be at 4 p.m. Pacific, 6 p.m. Central, 7 p.m. Eastern. Come on by, get help, math, science, all types of fun stuff. What we're gonna do now is we're gonna go raid. Let's go raid Penn Center. So Penn Center's doing abstract algebra. So go say hi to our friend Penn Center. He's a lot of fun, and you can go learn about abstract algebra with him. Otherwise, have a wonderful rest of your Monday. Have a great start to the week, and we'll see you guys tomorrow. Cool. All right. Peace out.
Okay.
All right. Peace, Sensation.
Examples. Why Wikipedia is always way too much for me. Okay. Fourth. Okay, so it has to be a linear map.
Zeta close! Just a few definitions away. Homomorphisms map structures while preserving operations. Keep your calculations sharp, and you'll be
We
there
did
in
it
no
in chapter
time.
6. Permutation groups. I'm pretty sure we did isomorphism.